I want to continue. Last time we were talking a little bit about patterns in carbonyl chemistry, and one of the things we talked about was carbonyl mechanism steps. And we mentioned that we can categorize every step within a carbonyl reaction mechanism as to one of three things. Now, what I mean by this is not if you have a carbonyl, what are the carbonyl fates? This is a little bit different than that. I'm saying that every single mechanism, every single step in a carbonyl mechanism, whether or not the carbonyl is present in that step, can be categorized as one of three ways. And I'm bringing this up again because as we continue to talk about mechanisms, this is a useful pattern. So those things where, does anybody remember? Maybe you can even do it without looking at your notes. Proton transfer, that's one of them. PT, which means something completely different to ROTC people. Aren't they ROTC people here? No, PT. This is what you do at 4 a.m. Physical training. For us, it means proton on, proton off. Proton transfer. What else? Pull out a carbonyl mechanism, say the Fischer esterification mechanism or the imine formation mechanism, either one of those. As you go through the steps, every single one of those steps, which is not proton transfer, is one of two other things. Nucleophilic attack of the carbonyl, right? And the third one is ejecta leaving group tetrahedral adduct decomposition. And that's usually going to mean ejecta leaving group. So bear that in mind when you're doing a mechanism, a carbonyl mechanism, you don't know what to do next, it's pretty much going to be one of these three. Now, there is a third. This was the second of our pattern issues that we talked about last time. There's a third pattern issue that I want to talk about, and that is this guy, proton transfer. We can call this carbonyl to protonate or not to protonate. That is indeed the question. I'm not going to go into slings and arrows and that kind of thing for those of you who know the, right, the whole quote? I don't remember the whole quote. The quote I'm asking, not the quote, the mechanism I'm asking, it's Friday, it's been a long week. The mechanism issue I'm asking about here is protonating the carbonyl. Some of the mechanisms we did, as a matter of fact, many of the carbonyl mechanisms we've done up to this point have begun with nucleophilic attack on the carbonyl. Some of the other mechanisms on the other hand, off the top of my head, the Fischer esterification, started with protonation of the carbonyl. So the question becomes, when do I have to protonate the carbonyl to start the mechanism, or when can I get away with it? Well, there are a number of things that influence that. One is the presence of strong acid. It takes strong acid to protonate a carbonyl. H2SO4, H3O+, that kind of thing. A protonated alcohol if the alcohol maybe is your proton bus. Weak acids, water, methanol by itself, that kind of thing, not sufficiently acidic to protonate the carbonyl. You also have to think about the carbonyl's electrophilicity. More electrophilic carbonyls will accept a nucleophile without the need for protonation. Less electrophilic carbonyls may have to be protonated. You may also have to think about how good is the nucleophile. Good nucleophiles usually don't require the carbonyl to be protonated first. Lousy nucleophiles usually have to protonate the carbonyl first. Now, in many circumstances, you're going to be kind of in the middle on the fence and say, well, I don't know if this carbonyl is electrophilic enough. I don't know if this nucleophile is nucleophilic enough. So really, this is the thing to look for. If there is strong acid present, use it. You won't get a wrong mechanism if you protonate the carbonyl with strong acid before you add the nucleophile. That assumes, by the way, the acid and the nucleophile are together at the same time. We're going to see other cases where acid Strong acid is used in the reaction, but not in the same step as the nucleophile. So if you protonate the carbonyl first, if strong acid is present, you'll come up with a good mechanism. Now, in some cases, like the imine formation mechanism we talked about last time, you can still come up with a good mechanism without protonating the carbonyl first. Or if you do protonate the carbonyl, you'll also come up with a good mechanism. So when in doubt, if strong acid is present, protonate it. Protonate the carbonyl to begin with. Now, that brings up another question. How do we think about the role of acids and even bases in this whole kind of thing? So I want to shift to talking about catalysis, and that's actually what we have in our lecture supplement for today. So let's off. There we go. All right, so part of the reason we're talking about this is because we've actually run into a bunch of carbonyl reactions so far that have been catalyzed, but also because catalysis of carbonyl reactions is ubiquitous in biology. It's all over the place. There's dozens and dozens and dozens of examples of enzymes operating on carbonyls where the mechanism involves acid and or base catalysis. So let's talk about these kind of processes. Let's start with reminding ourselves what the catalyst is. This is something which alters the reaction pathway, alters the mechanism, so that the energy of activation for the rate determining step is low enough that the reaction can go faster. Otherwise, catalysts make reactions go faster. Also, by our definition, catalysts are regenerated at some point in the reaction, often in the last step, and it doesn't have to be regenerated in the form that you've added it to the reaction. So, for example, you might have a reaction in which H3O plus is the catalyst, but the reactants that you use are H2SO4 and H2O. You haven't added H3O plus. Those guys mix together to make the H3O plus. So you may only have to use a little bit of H2SO4 to make the little bit of H3O plus you need. But in that case, it's the H3O plus. It's the actual catalyst. Now, how in carbonyl reactions can catalysis happen? Well, one of the ways it can do is by enhancing the reactivity and maybe a little more precisely the energy or stability of the carbonyl and or the nucleophile that is involved. And that can enhance the rate of the reaction because we're playing with energy. If you remember, if you change the energy difference between the reactants and the transition state, energy of activation changes, rate changes. Now, you can also influence the position of an equilibrium by causing perhaps a shift to the product or a shift to the reactants in maybe one mechanism step or the whole thing. Now, that's not really what a catalyst does, right? That's not a role of a catalyst. A catalyst, in principle, doesn't change the equilibrium constant. But it can help move one mechanism step forward by making, for example, the reverse step not as favorable. Enzymes also can do this kind of thing. But it's really in terms of the rate, it's by altering reactivity, altering energy. Now, again, just as a reminder, here is our generic carbonyl mechanism box. We had it in a red box last time. So we have the addition to the carbonyl to give the tetrahedral adduct, which can either eject a leaving group or be protonated. So those two possibilities, add to the carbonyl and then carbonyl ejecting a leaving group, are both potential places for catalysis. We're not too worried about the protonation here because that's not rate determining. Now, to think about how this process might work, let's talk about an actual carbonyl reaction, and that is the conversion of an amide, a hydrolysis of an amide with water to a carboxylic acid and an amine. It's a kind of a generic substitution reaction. It very much follows this kind of the substitution mechanism, add some proton transfers to finish it, and I encourage you to draw it out. And in the process of drawing it out, identify places, mechanism steps that are difficult, energetically expensive, the kinds of places that you might, if you were trying to make the reaction faster, you might apply catalysis. But we know that this hydrolysis is virtually doesn't occur at room temperature with just water and amides because, as we said before, amides are in proteins, and proteins just don't fall apart all by themselves in water. Now, how could we make this particular reaction go faster? Well, we can do it with acids or bases or enzymes. So let's talk about bases first. Now, how might a base catalyze a reaction? Well, a base isn't going to catalyze a reaction. The base will catalyze the reaction usually by taking the nucleophile and making it into a better nucleophile. So up here in our peptide hydrolysis mechanism, water is the nucleophile, not a terribly great nucleophile. But if we were to take the proton away from that nucleophile and convert it to its conjugate base, so in this case it'd be water into hydroxide, hydroxide's a better nucleophile. And so the nucleophilic attack on the carbonyl occurs more quickly. That's this step in the mechanism. But also because hydroxide is a poorer leaving group than water, the mechanism then has a greater incentive to go forward than it does to go backwards. All right, so how does that exactly work in this particular case? Well, water is going to react with whatever the catalyst is, whatever the base catalyst is. And it doesn't necessarily, well, we don't know what the catalyst is. We're being generic. But it's going to take the proton away from the water to make hydroxide. Hydroxide does the substitution reaction. And remember, the carboxylic acid that's produced is going to become deprotonated because the hydroxide is a good base. And then the catalyst ends up, because it comes out of this as being protonated, it ends up having to be deprotonated to regenerate the catalyst cycle. Now, to be fair, in this particular reaction, if you write it out, the hydroxide really isn't catalytic in the traditional sense, meaning the hydroxide doesn't get regenerated at the end. It actually gets consumed, making this carboxylate. A carboxylic acid here gets deprotonated to make the carboxylate. But if you have a little bit extra hydroxide, you can kind of think of that as the catalyst. So sometimes we might call this base promoted instead of base catalyzed. But again, hydroxide doesn't even necessarily have to be the base/nucleophile. It could be something else. But overall, the mechanism faster with hydroxide than with water because hydroxide is a better nucleophile. And I encourage you to work out the complete mechanism and see how the catalyst works in this particular process. All right, next page we talk about a kind of catalysis for carbonyl reactions that we've actually already talked about to a certain extent, and that is acid catalysis. Now, acid catalysis certainly isn't going to make the nucleophile more nucleophilic. If you take a nucleophile and put a proton on, you're taking electron density away from the nucleophile, so that's going to hurt it. But it can enhance the electrophilicity of the carbonyl. This is exactly what we did in the Fischer esterification. So if we protonate the carbonyl, now it is more susceptible to nucleophilic attack, and because the tetrahedral intermediate is less reactive, it can be a little bit more selective in what leaving group it kicks out. But it's the enhanced electrophilicity of the carbonyl that's the main issue here. And a reminder that to protonate a carbonyl, you need strong acids, H2SO4, protonated water, protonated alcohol, that kind of thing. And alcohol or water by itself, not good enough to do that. Now, the reaction, again, is accelerated because of the carbonyl electrophilicity we talked about and the tetrahedral intermediate, which we just talked about. All right. So here's, going back to our peptide hydrolysis, what might happen. Well, water was the nucleophile. And if we protonate the water, that certainly hurts it in terms of nucleophilicity, but then we can use the H3O plus to protonate the carbonyl, so the water is being the proton bus. And the protonated carbonyl is more susceptible to nucleophilic attack, just like the Fischer esterification kind of process. So again, reaction slower without H3O plus if it's just water, and I encourage you to work through the mechanism. Note that the H3O plus can in principle be regenerated again at the end. The mechanism for the amide hydrolysis under acidic conditions is very much like the mechanism for the Fischer esterification under acidic conditions, which is very much like the ester hydrolysis under acidic conditions. See the pattern? When you have a carbonyl and you're doing a substitution reaction under acidic conditions, they tend to be pretty much very similar mechanisms. Maybe the sequence of the timing of the proton transfers is different, the leaving group and nucleophile are different, but overall, a great deal of similarity in those. Now, let's talk about enzymes. Enzymes generally don't do catalysis by using strong acids and strong bases. There aren't things of the nature of protons in an enzyme that are as acidic as sulfuric acid floating around your body, generally because there's lots of water in your body, which would take those protons away. There are weak acids and weak bases. But enzymes do a whole slew of things to catalyze reactions. There is, every time I do this, I keep thinking you should find this. There's a paper that was published a bunch of years ago, a review, that says here are all the ways that enzymes have been suggested to catalyze reactions. And there's something like 50 different ways. I keep wanting to put it up here and say, look at all these ways. But some of the more common things that you might see are, number one, this organization where the enzyme will get the reactants pointed in the right direction so that they can react. Remember, for a reaction to occur, the collision between the two reactants has to occur with sufficient energy, but it also has to have right orientation. And the orientation, for the most part, is simply a matter of making sure that the appropriate orbitals point in the right direction. It is, to use the metaphor I've used before, and I will probably use again, like a sixth grade dance. How many of you remember sixth grade dances, right? How many of you didn't remember sixth grade dances until this class, and those suppressed memories have come back like a horrible tsunami? Right? Remember, one side of the gym, the boys, the other side of the gym, the girls, and they kind of look at each other. They don't know what to do until the chaperone comes along and grabs little Janie by the hand and little Billy by the hand, brings them to the middle of the room, points them in the right direction, and kind of gets them spinning around and says, see, that's how you do it. So the chaperone is kind of working like the enzyme. It's getting them pointed in the right direction to get things started. Now, another way that enzymes may interact and cause reactions to go faster is by stabilizing transition states. Now, this was Linus Pauling's idea. Remember, this is Linus Pauling of hybridization, Linus Pauling of electronegativity, Linus Pauling of resonance, Linus Pauling of DNA as a triple helix, Linus Pauling of Nobel Prizes, Linus Pauling of vitamin C of Caltech, Linus Pauling, that Linus Pauling. All right, by the end of Chem 14 series, certainly it's one name you ought to know. That and the name of your TA. I'd suggest knowing your TA. They probably have a little more influence on your learning than Linus Pauling did. But anyways, Linus Pauling suggested that one way in which enzymes may catalyze reactions and make them go faster is to change the energy of the transition state. So imagine we have some reactants. We got a transition state. The energy difference between them controls the rate of the reaction. But Pauling's idea was maybe the enzyme stabilizes the transition state by hydrogen bonding, dipole-dipole interactions, whatever, all those non-covalent interactions we've learned about. So if you stabilize the transition state, the energy of activation goes down and the reaction becomes faster. As a matter of fact, we use this in some drug design now. There are drugs that are designed to look like the transition state, and the enzyme says, wow, I really like that, and it binds to them and it blocks the enzyme. But another thing you can do along these same lines, if you're manipulating the energy of activation, in addition to or instead of lowering the transition state energy, you can raise the reactant energy. Well, how would you do that? Take a polar molecule and put it in a nonpolar environment. If it's a cyclohexane, force it to be a boat if it wants to dock to the enzyme. Those kinds of things make it uncomfortable and raise its energy. And if you raise the energy of the reactants, energy of activation goes down, reaction becomes faster. So there's a whole slew of other things that can happen. Those are two of the more common ones. Now, when we talk about rate enhancement here, what do we mean? Rate enhancements of up to about 10 to the 28th compared to non-catalyzed reactions are known for enzymes. These are really big numbers. Let me give you a typical number. A 10 to the 9th rate enhancement, which is not a really big one, especially where, a billion doesn't mean anything to us anymore, at least not in this country or this state. There was a time we go, wow, $1 billion, that's a lot. So what does that mean? A rate enhancement of 1 billion, 10 to the 9th, if you take a reaction that's catalyzed, whose rate is accelerated by 10 to the 9th, compare that to the non-catalyzed event. That catalyzed reaction turns over once every second, whereas the non-catalyzed reaction only turns over once every 32 years. Now, imagine you had reactions in your body that you needed to live that only happened once every 32 years. And that's one molecule once every 32 years. That would be kind of difficult. So these rate enhancements are important. Now, in the peptide hydrolysis case, how does this work? Well, there's our amide that we're going to cleave again, and water is the nucleophile that we need to use the cleavage. There's the OH of the water and the H of the water. And again, by itself, water, not a good enough nucleophile, not sufficiently acidic to do acid or base catalysis, but we can add an enzyme, let's say chymotrypsin, and that will do this catalysis, that will cleave this very nicely. Now, chymotrypsin happens to be an enzyme which doesn't cleave every amide. If it cleaved every amide, that would be a problem because then it would just start chopping up proteins at random. We don't want that. Chymotrypsin is fairly selective for the carbonyl, for the phenylalanine carbonyl side of amides. So in other words, there's our amide linkage. It's holding a bunch of amino acids together in the protein. There is a phenylalanine amino acid, so there's the carbonyl, there's the nitrogen, there's the alpha carbon, and chymotrypsin likes to cleave right along that bond. Now, what we're going to talk about on the next page is the mechanism for this process. And as soon as we mention enzyme mechanism, some students get very scared. Think, oh my God, this is biology, this is complicated. It's true, it is biology. And yes, biology can be complicated. But biology, biochemistry, is just organic chemistry with bigger molecules and more abbreviations. But it's still the same kind of molecules with the same kinds of functional groups and the same kinds of mechanisms. So in many, many, many circumstances, I can't think of any exceptions, can we not look at a biochemical process and say, oh, here's the mechanism, here's how it works. So we're going to do the same thing here. Now, I'm not asking you to memorize structures. That's not the purpose of this. What we're going to do is look at this and see what we've already learned about carbonyl mechanisms. How does that apply? Where is the catalysis happening, etc.? All right, so here's the process. Here, the wavy line represents kind of the peptide backbone. It just holds for our purposes here, just holds the rest of the enzyme together, unimportant. What's important is these amino acid side chains. There's a glycine side chain. Actually, this is a glycine NH. There's a serine side chain, which is a CH2OH. There's a histidine side chain, which is that imidazole, and then an aspartate side chain, which is a carboxylate. They stick down into the active site of the enzyme and actually do the chemistry. This is part of why when we talk about amino acids, we spend so much time categorizing the side chains, because that has a lot to do with how they actually carry out chemistry. Now, one of the first questions we might ask is, why is this enzyme, the chymotrypsin, specific for phenylalanine? And that is because this enzyme has a little pocket over here on the side, a hydrophobic pocket. It's kind of a non-polar area. And the thing that's being chopped up has to kind of dock in that space before the enzyme will accept it and operate on it. So this little cleft puts the phenyl CH2 of the phenylalanine, which is all hydrophobic. So hydrophobic likes hydrophobic, and that pocket is the right shape. So that's how the enzyme, kind of working its way down the protein, kind of feeling its way down the protein, goes, aha, this piece has the right shape and size and hydrophobicity. That's what I want to link onto, because that's going to tell me I need to cleave next door. So how does the cleavage actually occur? Well, there's our amide. And of course, to do cleavage on this, to do the hydrolysis, excuse me, we need to do the nucleophilic attack on the amide. Well, what are our choices to do that with? The way it docks, we have the serine CH2OH, which is not a great nucleophile. So how do we make the nucleophile better? Base catalysis. Take the proton away. So that's what happens here. The imidazole, this 5-membered ring with 2 nitrogens, that's also aromatic, takes the hydrogen away from the serine. Now, at the same time as that hydrogen is being taken away, the oxygen is beginning to build up a negative charge. It never gets to the full negative charge stage. You can turn around and attack the carbonyl of the amide right away. And you might say, wait a minute. Didn't you tell us several times you can't have 3 things banging together at the same time? This would be imidazole and serine and amide all coming together at the same time. Well, in fact, it's essentially just one thing, because the imidazole and the serine are together in the enzyme. They're covalently bonded to each other, and the substrate is already non-covalently bonded, but it's held right there. It's not going anywhere. If I may use a metaphor that I just thought of, let's see if it works. Imagine you have to feed your baby. Right? Here's your bottle. You know, you've got the milk in here, and you put it on your wrist just to make sure it's not too hot, etc. And you're going to feed the baby. Now, if the baby's running around, you've got to chase after the baby before the bottle can go into the baby's mouth. On the other hand, if you're holding the baby, the bottle goes right in, because you're together with the baby. The baby is bound to you like the substrate is bound to the enzyme. And here comes the nucleophile, the bottle. Much easier to feed the baby if you're already holding the baby. Does that metaphor work? If it does, that's great. If it's not, just blot it out of your mind. But this thing can easily do that attack. All right, so now we have our O- essentially attacking the carbonyl. Do nucleophilic attack on a carbonyl. What does that give you? The same thing it gave us so many other times. Nucleophilic attack on a carbonyl gives a tetrahedral adduct, in this particular case with a negative charge on the oxygen. Now, in the early days of this mechanism, people looked at some of these other hydrogens around here where the carbonyl is and said, maybe there is some acid catalysis that's happening at the same time. Now, these NH bonds that are here are certainly not acidic enough to protonate the carbonyl, but maybe they do it through hydrogen bonding. It's kind of the same thing, except instead of giving the oxygen a full plus, you give it a little bit of a delta plus through hydrogen bonding. Well, good idea, but it turns out these guys are too far away to do that. But when we get up to the tetrahedral intermediate, now it turns out they're close enough to hydrogen bond with the O- and stabilize the tetrahedral intermediate. That's kind of Pauling's idea, right? This transition state would be stabilized by the hydrogen bonding growing in. But still, regardless of the stabilization, it is a tetrahedral intermediate with a negative charge on the oxygen. And this is about the umpty-ump millionth time, especially if you've been doing practice problems, that you've seen a tetrahedral intermediate with a negative charge on the oxygen. Bree, I know you lost count of how many times it is. It was like a gazillion last time. What are we up to, 2 gazillion now? Something like that. But a tetrahedral intermediate with a negative charge on the oxygen, it likes to, let's say it together. All right, it's Friday, you're tired, I know. Eject the leaving group. That's the first thing it tries to do. All right, what are our leaving group possibilities? It could eject this side chain, the CH2CH2 phenyl will eject that. No, when are carbon groups leaving groups? We pretty much don't see that. It could eject the serine O- that just came in. That can certainly happen, but that's not productive. So what's left? The nitran ion, which is what we have to have leave anyway. So this is going to leave. We reform the pi bond and the nitrogen leaves. But we know that nitran ions are not the world's best leaving group, especially if there's no resonance stabilization of that negative charge. That's why they can only leave under special circumstances. But no problem. That's what we have enzymes for. The enzyme is going to, in the transition state, as that nitrogen is beginning to build up its negative charge, the enzyme is right there to protonate it. So this hydrogen that we took away from the serine, we put on the imidazole, we're going to put it back on the nitrogen. It's kind of like as the nitrogen is leaving, it's really upset because it's getting a negative charge, and the imidazole is right there to pat it on the back and say, there, I will make you feel better. Here's a proton. It's like the baby that you're trying to feed, right? All right, so that's going to give us our imidazole back. See, there's the catalysis. Unprotonated, protonated, unprotonated, so we've regenerated our base. We have the amine group is left, so we've chopped our amide, and now we have a problem, though, because the serine OH is now attached to an ester. Now, the job, we've cut the protein, we've hydrolyzed the amide, and that's good. But the problem is if an enzyme is going to be a catalyst, it has to be regenerated. We've got to be able to reuse it. You know, it's got to be green, so to speak. Not much point in having an enzyme to catalyze a reaction if for every time you want to chop up the protein, you have to manufacture a whole nother molecule of enzyme. That'd be very wasteful. So what we need to do is cleave this again to get our serine free to go back where we came from. But it's just hydrolyzing an ester. It's very much like hydrolyzing the amide. We just need, instead of using the serine to do it, since the serine is bound, we're going to use a molecule of water. But once again, here's the catalysis. The base deprotonating the water to make the stronger nucleophile at the same time, in this case, that it's attacking the carbonyl, exactly what we saw up here. There's attacking the carbonyl. That takes us up to a tetrahedral intermediate with a negative charge on the oxygen, once again stabilized without hydrogen bonding. Tetrahedral intermediate with a negative charge on the oxygen, so it will eject the leaving group. What are our leaving group choices? The carbon group? Nope. Hydroxide? It could. That just take us back where we came from. Or it could eject that serine side chain, which we have it doing here. Now, here it's shown as 2 steps. The O- then picks up a proton, or you could combine this ejecting step with the deprotonation, just like we did over here. Either one is fine. But it gets us back to where we started from. So all the protons are back, all the groups are back where they were to begin with, and the enzyme has cleaved the protein, and it's ready to start the cycle again. So the catalyst is being regenerated. Now, this is a somewhat simplistic description of how this happens. There's some other things that go on. But overall, it's just an amide hydrolysis with acid and base catalysis going on. pretty much the same kinds of mechanisms we've been talking about. So when you get to biochemistry and you start talking about enzyme reactions and all that other kind of stuff, bear in mind that they pretty much use exactly the same kinds of principles that you've learned here in 14D. All right. Now we're done with our lecture supplement there. All right, now we still have one major area in carbonyl chemistry to talk about. We have talked about reactions in which we've done addition and substitution, and we've made new carbon-oxygen and new carbon-nitrogen bonds, but we haven't talked about making new carbon-carbon bonds or new carbon-hydrogen bonds. Now, making new carbon-carbon bonds is of particular importance if we're doing organic synthesis. If we're taking simple molecules that Mother Nature provides for us, so we can buy in large quantity, and want to make things more complicated. Oftentimes, synthesis involves building up the carbon-carbon skeleton. For example, way back in the beginning of 14C, you may have remembered Taxol. That comes from, if you're going to make that in the laboratory, much simpler molecules, but you have to add lots of carbon-carbon bonds to do that. So can we use carbonyls to make carbon-carbon bonds? And the answer is absolutely. As a matter of fact, carbonyls give us some of the most useful strategies for making new carbon-carbon bonds. So let's talk about that. New carbon-carbon bonds. Now, in a generic sense, here's what we'd kind of like to do. Take our carbonyl, and I'm not going to specify which carbonyl functional group it is. And I'm going to illustrate this as an addition, but you can kind of also think about this as a substitution process as well. What I would like to do is make a new, I'll just call it CR3 down here. Right there, that's what I want to do. Make a new carbon-carbon bond. Now I'm making it at the carbonyl carbon, which means this piece that I'm bringing in, it's going to come to the carbonyl. In a generic sense, this thing that I'm bringing in, that I'm going to react with the carbonyl, has to be a, what do you think? How many of you are Monty Python fans? Right? Remember the knights who say, nee, nee? What they were trying to say was, nucleophile. And by the way, if you're a fan of Monty Python and the Holy Grail, you'll like to know that they beat cats 27 times in that movie. Most of them you can't. There's scenes that throughout the movie where either you can see the people or hear cats being beat. Not that I'm a fan of beating cats, of course, but just that's a statistic that people would like to know. So this needs to be, whatever I'm going to add here has to be a nucleophile. So in other words, what we want, if we're going to use carbonyls to make new carbon-carbon bonds, we need nucleophilic sources of carbon. Now we've talked about a lot of nucleophiles, but only one so far have we talked about, which is a carbon nucleophile. Anybody know? I'm sorry? Well, we did talk about pi bonds, that's true, but they don't add the carbonyl. Good nucleophile. It's Friedel-Crafts, so that's the benzene ring is a nucleophile. Okay, we talked about several examples with crappy nucleophiles. I mean a good nucleophile. That's what I get for teaching you so well, right? Mental note, don't teach them so well next time so they can answer the question the way you want it answered. I'm sorry? C triple bond N, cyanide, yes. Remember way back to SN2 days, cyanide ion, good nucleophile. Now it's true we did talk about carbon-carbon pi bonds as nucleophiles, but again, they're pretty lousy and they generally don't react with, especially normal carbonyls. So what about cyanide? Could cyanide be a nucleophile to add to a carbonyl? And the answer is yes. Here's an example of it. We could take acetone, for example, and Cn- cyanide. And because acetone does not have a leaving group, we can only do an addition reaction. You can do substitution reactions on carbonyls with cyanide as well. And this will require some sort of proton source to put the proton on the oxygen. And it turns out HCN, the conjugate acid of CN, is a good way to do that. So that's our reaction overall. This thing we're making is called a cyanohydrin. There's the cyano of the cyanohydrin. And actually, from a synthesis point of view, it's kind of useful because it's got an OH and a nitrile, and You can operate on the OH, you can operate on the nitrile, etc. All right, so what's the mechanism for the process? How does it occur? Well, we have some reactants that we can start with here. Cyanide and HCN. Now, we talked a little bit about putting the proton on the carbonyl. So do we start the mechanism with nucleophilic attack on the carbonyl? Or do we start the mechanism with protonation of the carbonyl? Let me give you a hint when I find the exact number I'm looking for, which I can't find, so I'll take a guess. The pKa of HCN is 10. Remember, pKa is a measure of acidity. 10, not all that strong of an acid. It's certainly weaker than acetic acid, but a stronger acid than water. Now, acetic acid's got a pKa of about 4.8. Is acetic acid a good enough acid to protonate a carbonyl? No, and this is a lot weaker than that. So while HCN is an acid, it's a kind of a lousy one. So we can't start with protonating the carbonyl. So what are we going to start with? Nucleophilic attack. There's our tetrahedral intermediate with a negative charge on the oxygen. And before, hopefully at this point in the course, before you even finish drawing that tetrahedral intermediate with a negative charge on the oxygen, probably when you've made this stroke, this circle, and this little stroke, you're thinking, aha, I am going to eject a leaving group. What are our leaving group choices? Methyl group? Never ever. Methyl group? If this one doesn't leave, that one isn't going to leave. Cyanide. Cyanide turns out to be a pretty lousy leaving group. It can be kicked out of the O-, but that's kind of irrelevant because it's not going to move the mechanism forward. So if we don't have any leaving groups that we can kick out to move the mechanism forward, what do? We put a proton. What is our proton source? Go back to our reaction. What is our proton source? HCN. O- is a strong enough base by about 5 orders of magnitude to easily deprotonate that. And this will reveal why we use HCN. So there's our deprotonation. OH. There's the CN that we added. And what's the other product of this mechanism set? CN-. How about that? I've regenerated the nucleophile. Now, it turns out for practical reasons, we usually don't use HCN. I'm going to put that in parentheses. Usually what we use is we take cyanide, we have an excess of cyanide and a little bit, a catalytic amount of something like H2SO4. And that will protonate a little bit of cyanide to make a little bit of HCN. The reason we don't do that is we know cyanide is a nasty, nasty, nasty poison, right? You don't, when you're done setting up this reaction, you don't lick your fingers off. HCN is like CN-, except this is a gas, which means you got to use extra special precautions to handle. This is a solid potassium cyanide, not as much of a problem. This is a real pain in the butt. So we try to avoid that in the laboratory by just using a little bit of H2SO4. But mechanism would be the same. So that's our addition mechanism. Now, this is great if you want to make a new carbon-carbon bond. And this works with aldehydes and ketones, and you can even do substitution reactions with acid chlorides and things like that. But it's got a significant drawback in that if you want to have more than one carbon to add, you've got to manipulate the cyanide, which is a couple of extra steps. So it would be nice if we had a nucleophile we could bring in a whole bunch of carbons. Well, there is a nucleophile that's good at that. And that is alkyne anions. So that's something like this. It's a carbon-carbon triple bond with a lone pair and a negative charge on one end and almost whatever you'd like on the other end. Good nucleophiles because, well, the carbon-carbon triple bond is skinny. It can get into little places, but perhaps more importantly, this negative charge is localized on that carbon. There's no delocalization through resonance. Yes, there's a pi bond here, but remember, to delocalize a lone pair, you have to be one carbon further removed. This would have to be one carbon further out, not here. So good nucleophile. Now, the first question is, where do these guys come from? They come from taking the corresponding terminal alkyne and deprotonating it with a strong base. And you use pretty strong bases for this. Frequently we use sodium amide. That's the conjugate base of ammonia. It's a really strong base to use. Industry likes to use it because it's cheap. So that makes this anion, and then once we have this, this is a good nucleophile that we can add to our carbonyl to make a new carbon-carbon bond. For example, well, let me illustrate it with a thought question. Let us imagine we wanted to convert acetone into, let's say, this guy. So there is our new carbon-carbon bond. And the fact that the new carbon-carbon bond is on the carbon that already has an oxygen suggests a nucleophilic carbonyl addition kind of strategy. And so this is the piece we're going to add. We need 3 carbons. So how would we do that? Well, let's start by taking the alkyne. And you deprotonate that. So there is our deprotonation process. Now this is a good nucleophile. So now in our next step we can add the electrophile, which is the acetone. Here's our acetone. Nucleophilic attack on the carbonyl, just like we've seen happen so many other times. Which gives us a tetrahedral intermediate with a negative charge on the oxygen, which will try to eject a leaving group. Methyl groups, no. Alkyne anion turns out not a leaving group. So nothing to go backward, no leaving group here. So what do we do next? And we put a proton on, and that is going to make our final product here. New carbon-carbon bond right there. So the overall process, if you want to start with the alkyne, is step 1, put in the base. Step 2, put in the carbonyl. Aldehydes, ketones, acid chlorides, esters, much less reactive than an ester, and it doesn't work. Amides turn out are pretty resistant to this kind of thing. But the more reactive carbonyls will do this. And then step number 3, put a proton on. Very useful because there's the piece I've added. And I can, as long as I can come up with the alkyne, I can make the anion. So I can have, in principle, pretty much whatever I want. On top of that, I have a new carbon-carbon triple bond that I've added, so I can do all sorts of carbon-carbon triple bond chemistry. So there's a lot of flexibility here. This is a nearly perfect strategy for making new carbon-carbon bonds, as long as you don't mind the triple bond and as long as you don't mind the OH. There's ways to get rid of both of those. But what happens if you want to add just 1 carbon? It's like a Lay's potato chips. You can't add just 1. Imagine you want to do this. You want to convert acetone into tertiary butyl alcohol. We have 2 methyls to begin with. They're going to add another methyl, add 1 carbon. The cyanohydrin strategy, well, that could work. It only adds 1 carbon, but then I have to do everything to convert the nitrile into a methyl group. Extra steps. I can use the alkyne strategy, but then I have to throw away at least 1 carbon because the alkyne is always going to add at least 2 carbons. So what we need is some strategy which will allow us to add 1 carbon. Now it also turns out that strategy allows us to add pretty much any number of carbons we want. It's even more versatile than the alkyne strategy. We'll leave that till Monday.